So the first speaker of the session is Sebastian Gomez from STSCI, and he has a contributed talk on optimizing the search for exotic transients.
Hey, thanks. I'm assuming you can see my screen?
Yes.
Yeah, well, thanks for having me. I am Sebastian Gomez. I am a postdoc at Space Telescope and also a member of the newly formed Transient Science at Space Telescope group, TSST. And I'm going to tell you a little bit about the search for exotic transients, where exotic transients means tidal disruption events and superluminous supernovae, also put it in the context of Roman. So I've broken up this talk in 3 rough parts. I'm going to tell you a little about the context of how we have been using machine learning to find superluminous supernovae more efficiently, about current efforts to apply these methods to the search of tidal disruption events, and how this applies to Roman. So superluminous supernovae, like their name suggests, are very luminous supernovae. They used to be classified based on anything that was brighter than some threshold, but then we started finding them at different thresholds. So now they are classified based on their spectra, and they are much brighter, up to 100 times brighter than normal supernovae. And one of the main questions about them is what powers them? Because we know that normal supernovae are powered by the radioactive decay of nickel-56, at most a solar mass of nickel. So maybe you are inclined to think that superluminous supernovae are just powered by more nickel. It turns out this does not work because the amount of nickel you would need to power a superluminous supernova is prohibitively high and completely inconsistent with late-time observations. In this case, 28 solar masses and less than a third of a solar mass. So instead, it seems that superluminous supernovae are a different thing. They are powered by some other mechanism. The most likely one seems to be a magnetar central engine, which is just a very fastly spinning neutron star at the center of the ejecta. And as it slows down, it deposits this spin down energy into the ejecta, powering the optical light curve. And we managed to reproduce the high brightness of superluminous supernovae. The spectra also coincide well with this model, and the late time observations of superluminous supernovae are also consistent with a magnetar. But today I'm going to focus a little more on how do we actually find them. And this is true not just for superluminous supernovae, but for any transient. If we want to understand them and study them, we need to find more of these objects. And superluminous supernovae are rare. In a magnitude limited survey like ZTF, if you were to just observe a random sample of objects spectroscopically, you would find that about 1.5% would be superluminous supernovae. And if your goal is to study those, that is not a very efficient way. So we want to increase this fraction or our efficiency at finding these exotic transients. That's why we developed FLEET, the Finding Luminous and Exotic Extragalactic Transients algorithm. And this is a machine learning algorithm that takes in any new transient detected, reported to the transient name server. It looks at its properties, its environment, where did it come from, how does its light curve look like, and then from those parameters, it assigns to each new transient a probability of being a superluminous supernovae, and that way we can better select which transients to follow up and hopefully find more superluminous supernovae. In this case, we found that features like the width of their light curves, superluminous supernovae, are very broad. Their time to peak, their color, and their normalized host separation, which is just how far away they are from the host galaxy where they happen, divided by the size of that galaxy. Those seem to be very important parameters. And another key here is that FLEET does not need a redshift, because a lot of these galaxies are not well characterized, and we do not have a redshift estimate for them. And the photoseas that we do have are usually pretty bad at this higher redshifts. So it's important that it works without the need for a redshift. And we started working on this over a year ago. We published a paper over a year ago. We have been running FLEET for over a year. These were the predictions that we got back then. These are curves of completeness and purity given a sample, and the probability of any new object being a superluminous supernovae. So if we were to say, I'm only going to observe things that are higher than 80% probability of being a superluminous supernova, then our completeness goes down to around 20%, which is cutting down a lot of objects. But the thing we care about the most is the purity, or that efficiency that we were talking about. That same 80% cut will get us about an 85% purity, as opposed to that 1.5% purity from just randomly observing objects. What this means in a real survey is that if you have like 1,500 transients in a month, that 1.5% means there's around 23 superluminous supernovae that are available to be discovered. And at this 20% completeness and 85% purity, that's around 4 superluminous supernovae a month, which is 50 times better than random selection. Those were our predictions. So how did we actually do? Like I said, we have been running Fleet since November 2020. Since then, there have been 37 superluminous supernovae discovered worldwide. Fleet found 13 of them. But what is a more important number is that 18 of those 37 superluminous supernovae were predicted by Fleet to be superluminous supernovae. So the other, 5 that we didn't observe, that can be observability problems. We just didn't have enough telescope time. We missed it, but we could have found them if we had had the instruments. But the point here is that the proof of concept worked. Fleet is finding superluminous supernovae, and we have shown that we can use this machine learning algorithm in a survey to find transients more efficient. Which brings me to my second topic, which is tidal disruption events. Now we want to use what we've learned from superluminous supernovae and apply it to tidal disruption events. Short gave a really nice introduction to what these are, so I'm not going to spend too much time. But tidal disruption events are when a star comes very close to a supermassive black hole. The supermassive black hole just tears apart the star, flinging about half the star away, and the other half gets circularized into an accretion disk around the black hole. And this event causes a bright transient that we observe. We can observe in the optical. Like with superluminous supernovae, TDs are very rare. These are even more rare than superluminous supernovae, since there are only around 40-ish well-characterized TDs that we know to date, and they show a wide variety of features that we don't really understand. So it's really important that we find more of them. Compared to superluminous supernovae, they are much rarer. They make about 0.5% of a magnitude-limited survey. So we train an algorithm to find TDs, the same Fleet algorithm, and we find that predictably, the most important things to look for when looking for TDs are that they have to be nuclear, meaning they have a low host separation because they happen in the centers of galaxies, and they are blue, unlike AGN, which also happen in the centers of galaxies, but those are red. So being blue and nuclear seems to be an important feature, but we also add properties of their light curves, like the rise time, the light configuration, the host color, etc. And we find that these are our predictions for how the TD version of Fleet might work. We see our completeness is pretty high compared to superluminous supernovae. We can get around 40% completeness if we make that same 80% threshold cut. And our purity is much lower than superluminous supernovae, mainly because there are just so much fewer TDs that we can train this algorithm on. But it's still remarkable that it gets above 50%. What this means for a survey is, again, with those 1,500 transients that you might get in a month, 8 available to be discovered with that 0.5% rate. That's around 1 to 2 TDs a month that we could find using Fleet on a survey like ZTF, which is 100 times better than random selection. And to conclude, I'm going to put this in the context of Roman, because all of this has been tested on ground-based surveys, but we want to know how this would perform on something like Roman. I am only focusing on the time domain survey. I am not considering the wide area survey or the galactic pulse survey. But in here, I ran just a simple simulation based on the nominal parameters that have been defined for the survey, which are subject to change. But I've defined a 16 square degree field of view, a 5-day cadence, 2-year duration in the middle of the survey, and 6 filters, 4 per mode. That white mode and deep mode that we heard about on the first day. The way the survey looks is it goes in a pattern and explores the entire 16 square degrees in the white mode, and then it goes in a little bit closer here, there, and it does the deep mode in another 4 filters, and every 5 days it does everything again. So now that we have this simulated survey, I can inject thousands and thousands of TDEs into the simulated survey, which I obtained from models of real TDEs. They are not just empirical parameters that we would expect for TDEs. These are real life groups of TDEs that I've oversampled and then fed into this Raman survey at random times, random positions in the sky, and random redshifts. And this is what we find. The gray are all of the TDEs that we injected into the survey, obviously normalized by cosmological volume. And then the green ones are the ones that were able to be recovered. So you see that we predict that we're going to find the most TDEs between a redshift of 1 and 2, with the highest fraction being around 30% of TDEs being able to be recovered. And here, recovered means just detected once, which is not very helpful, but just for the sake of computing this is just detected in one band, one time. If we want to get a little more use out of them, again, this is the same curve, the dotted one, showing that they peak between a redshift of 1 and 2 for any data points. And this is assuming a rate of 1 × 10⁻⁵ TDEs per year per megaparsec. I am willing to be given a better one if you have it. This is just a rough estimate. This would correspond to around 40 TDEs a year. But if we want anything that's well sampled, that would be, let's say, 20 points and a 70-day baseline. That brings us down to around 30 TDEs a year, which is still respectable. And if we were to implement something like Fleet, because not all of these are going to get spectroscopically observed, then we can recover around 7 TDEs a year from the survey, assuming a similar completeness and purity, bringing us a step closer to being able to find more of these objects more efficiently and make better use of our surveys. And with that, I will leave it open for questions.
Thank you very much for this nice presentation of this work. I don't see any question yet in Slack or in Zoom. So maybe I will ask a question. I was wondering, did you also do the, I mean, if I understood correctly, did you also do the analysis that if you tweak a little bit the Raman survey in terms of casings or filters, how much you could optimize?
Yeah, that is a goal right now. Right now, I just took the nominal parameters that we have, but I do want to see how this would change based on how we would change the survey, right? So if we increase the cadence, how much would that help? If we increase the area, how much would that help to try and motivate what parameters to change if it need? But yes, this is definitely something I want to do.
Then Ori Fox is asking, do you have similar results for simulation for the superluminous supernovas?
Yes. Yeah. You're asking if the TDEs in the supernovae are similar in Raman?
I think, Ori, if you can maybe unmute yourself, you may have maybe entered the talk too late because the first part of the talk was on superluminous supernova.
Yeah, maybe I missed it. When you showed the Raman simulation at the end, you showed the predicted rates with Raman for the TDEs. Do you have a similar slide for the superluminous supernovae?
I don't have a slide. I have some random plots on my computer. They're a little higher just because of tend to be brighter, so we can recover more of them, but the rough numbers are similar. Yeah.
Okay.
Okay, one last question from Ben Rose. What data alert stream is needed to use Fleet with Raman?
Sorry, I missed that. Can you repeat that?
What data or alert stream is needed to use Fleet with Raman?
Yeah, that is something that came up in the previous meetings of how Raman is not going to have like real-time alerts, which would be really helpful for this. But the good thing is that TDEs and superluminous supernovae are not fast-evolving transients. They last several months. So a 5 days response time is not terrible. So if Raman were to alert us of new sources within 5 days, it would still be useful. Here I am, all of these estimates I have are for the first 20 days of a light curve. So we still have plenty of time once the transient happens to be able to trigger it because they last a while. Okay,
thanks. A very quick answer, hopefully, to the last question now that is posted on Zoom. I'm from Seppo Matila. I'm wondering about possible effects of dust extinction for the TDEs detected rates with Roman.
Yeah, sorry, I didn't mention that, but dust extinction is added into the calculations. Yes.
Thanks a lot.